Okay, so in statistics 4.1, we're going to be discussing the scatter diagrams and their correlation. We're going to draw and interpret scatter diagrams. We will describe the properties of a linear correlation coefficient, compute, interpret the linear correlation coefficient, which is going to be what our R equals, and determine whether there's a linear relationship exists between the variables. And we definitely want to talk about the difference between correlation and a causation also. So a response variable, this is the variable whose value can be explained by the value of the explanatory or the predictor variable. So the explanatory is the variable that we're testing out to see if it explains the differences in that response variable in the end. So we're looking for those correlations between them. A scatter diagram, that explanatory variable is usually your x-axis and the response variables may be plotted on your y-axis. So with these two here, this one definitely looks like this is a positive linear relationship, and B looks like it's a negative linear relationship. But is it linear enough? Well, I don't know, and that's where we would use statistics to decide if it's actually linear enough or not. So this one here definitely looks nonlinear again, and no correlation. Now, we are only in an elementary level statistics class. If you were in an advanced class, you might be able then to try to prove, like for instance, this one here might be a quadratic regression or a cubic regression. But again, we're only in an elementary stats class, so we will only be discussing, is there a linear relationship or not a linear relationship? And again, like we said a minute ago, this one here had a positive correlation, and this one has a negative association. All right, so at this point, I need you guys to get your calculator, your formula sheet, your packet of notes. All right, once you have those items, go ahead and pause your video, come back. All right, so now that you have your calculator, your formula sheet, and your packet of notes, we'll continue. All right, so this data at the right shows the data is based on a study for a drilling rock. The researcher wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So the depth at which the drilling begins is the explanatory variable x. So in other words, this is saying they're like 35 feet below the Earth's surface, 120 feet below it, 175 feet below it. This side is going to give me the time in minutes and how much time it takes to drill an additional 5 feet from where I'm at. So if I'm at 35 feet below the surface, it's going to take me 5.88 minutes, to drill an additional 5 feet. And so like this one would be additional, it's going to take me 6.42 minutes to drill an additional 5 feet if I start drilling at 145 feet. All right, if we were to look at the scattergram of it, make sure you understand that they did put the depth at which the drilling begins. That's the one along here. Now they should have also added the unit measurement there of feet. All right, the y-axis was the time, was the in minutes. So they put time, and again they should have also put in minutes. All right, and here's your scatter plot. So it looks positive. Okay, it's kind of an upward trend, not real tight next to that line. Okay, it's definitely a little bit scattered off of it. All right, I will want you to put all these data values into L1 and all these data values into L2, and we'll be using those data values for this lesson of notes and also for 4.2. So when we're done with this lesson, you might want to copy the L1 and L2 into maybe like L5 and 6 so you have them ready for tomorrow's notes also. All right, so it looked like a positive association. So the properties of that correlation coefficient. All right, so remember that the Greek letters are the ones that talk about a population. So the Greek letter rho will represent the population correlation, and the regular letter, remember our regular letters, those represent the sample. Okay, so in this case, the sample correlation coefficient. All righty. So this one here, if you'll notice, this R is a perfect R equals 1. This R is 9/10. This R is 4/10. So notice as R got smaller, the points became a little bit more and more scattered. When R was 1, that was a perfect line. Here my R is -1, so notice now I have that negative slope, and again, they're still in a perfect line. This time, my R is the -9/10, and the R is the -4/10. So again, the closer it gets to 0, the more scattered your points are. Notice this one here, it says no linear relationship, and the R was close to 0. The points are all over the place. Even though this looks quadratic, we're not saying anything has a quadratic relationship. We're only doing linear or not linear in this class. So again, because this is just not linear, our R here was actually close to 0 if you do a line reg t-test, which is what we're going to be doing here today. So the properties, so again, if R is always going to be between -1 and 1, if it's +1, then it's a perfect positive linear relationship. If R is -1, it's a perfect negative linear relationship. The closer to 1 and -1 is, the stronger you have a positive or the negative relationship between the two variables. And the closer to 0 is just going to imply that there is no linear relationship. We're not saying that there's no causation. We're not saying that there's not a relationship. We're just saying there's not a linear relationship. Because it could be an exponential relationship, it could be logarithmic, it could be quadratic, there could be all kinds of other relationships. We're only testing in this course, is it linear or not linear? All right, this is the formula that you would use to calculate R, but we will be using our calculator to do this for us. So hopefully you already have these data values into L1 and in L2. If you do not, please pause the video and put them in. Again, put all the X's in L1 and the Y's in L2. All right, so welcome back from doing that. All right, so determine the linear correlation coefficient of the drilling data. So once you guys have put the data into it, you're going to push stat and you're going to move it over to test. There's only 3 kinds of tests we're doing this semester. We're doing the t-test if we're testing against the mean, against a population mean, an old one. We do proportion, the one proportion z-test if we're testing against like an old proportion. And now we're doing a line reg t-test. The line reg t-test is going to be, we're testing is the relationship between these two values. So we're going to go to stat, move it over to test, and then go ahead and down arrow all the way down to where you see line reg t-test. When you run that line reg t-test, I want you to make sure that your x's, that's your L1, is your independent variable. And your y's, those are in L2, that those are your dependent variable. They're the response variable. Once you run that test, you will always do it with a not equals. Again, advanced stats class would do a greater than or possibly a less than, but we will only run always, ours will always be is the not equal to, is the test that we're running. Now when you ran that, you got this R value of 0.7728215305. So that's definitely positive. It's pretty close to 1. It's definitely way closer to 1 than it is to 0. But see, is it close enough to 1 for us to say that there's a linear relationship between these two? And we'll be discussing how to figure that out here in a bit. This is the formula way to do it. I do not believe we have any desire in doing this formula way to do it. Okay, I just have the slide on there in case some of you want to do this. You would take each x value minus the mean of all the x's and divide by the standard deviation of the x's. So notice here I got the mean of the x is the standard deviation. And that's how I got each one of those. Okay, this column, again, you take each y value minus the average of all the y's, divide by the standard deviation of each of the y's right there. So there's the mean of the y's, the standard deviations. We do that for each value. Now over here, we take the product of them. So I take the product of this one, and that goes there. Then we add all those together. And then you divide by the n minus 1. There was 12 data points, so we divide by 11. And look at that same R that our calculator gave us a minute ago when all we had to do was run a line reg t-test. All right, so testing for a linear relationship. First off, we have to determine the value of the correlation coefficient. We just did that on that last problem. We're going to find the critical value for a given sample size. All right, so again, you're going to have your formula sheet out. And we're going to show you guys where to find that. Then, if the absolute value of that correlation coefficient, if it is greater than the critical value, then we say there's a linear relationship exists between the two variables. Otherwise, we just say there's no linear relationship. That's all we're doing, guys. Is there a linear relationship or is there not? There is, if our correlation coefficient is greater than the critical value, then there is a linear relationship. Otherwise, we say no linear relationship. So again, if the absolute value of R is greater than the critical value, then we conclude a linear relationship. So make sure you guys go ahead and get that written down somewhere because you're going to be referring back to that. And then go ahead and make sure you guys are flipped to chapter 4 notes on your formula sheet, please. All right, so determine whether the linear relationship existed for that drilling problem we just did. So we had 12 data entries. We found R to be 0.773. Now again, we had 12 data entries. So if you look on your formula sheet, you guys, I have included this table on your formula sheet for your test. At n equals 12 data points, this is 0.576 for my test statistic. Since that test statistic was 0.576, now see my absolute value of my correlation coefficient is greater than that test statistic. So if it is greater than, then there is a linear relationship between them. And then because this R was positive, we say that there is a positive linear relationship. If that R was negative, we would say there's a negative linear relationship. And again, the relationship between the time to drill an additional 5 feet from where you start at a certain depth for drilling, okay, at a depth at which the drilling begins. All right, so the difference between correlation and causation. So according to data obtained from Statistical Abstract, the correlation between the percentage of female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Yeah, that's pretty close to 1. Okay, so there's definitely a linear relationship between the percentage of female population with a bachelor's degree and the percentage of births to unmarried mothers. But see, one does not cause the other. I mean, just kind of common sense would tell you that. See, does this mean that the higher percentage of females with a bachelor's degree, do they cause a higher percentage of births to unmarried mothers? No, they wouldn't cause. So there might be a correlation, but it's definitely not a causation. So remember, we're not saying anything is caused here. We're just saying that there is or is not a linear relationship. We are not saying causation. Okay. All right, so another way two variables can be related, even though there's not a causal relationship, could be through a lurking variable. All right, so the lurking variable, that remember was related to both your explanatory and response variable. For example, ice cream sales and crime rates have very high correlation. All right, so does this mean the local government should shut down all ice cream shops? No. See, there's a lurking variable there of temperature. See, as the air temperatures rise, the ice cream sales increase, and so does the crime rates increase. Crime rates, if the temperatures are increasing, crime rates increase because people are usually a little more irritable. They are they're a little less patient, and they're apt to do more crimes. Well, and if the temperature is hotter, we're also apt to buy more ice cream. So we can't say that ice cream causes the higher crime rate, but we could say that there is definitely a relationship between the two. But see, we have that lurking variable in there of the temperature. See, the temperature, right? If we have an increase in temperature, my sales go up for ice cream. If I have an increase in temperature, then my crime rates rise. So again, we don't ever want to say cause here. We always want to just say that there is a relationship. Okay, it does not mean one causes the other. All right, so for this problem, because colas tend to replace the healthier beverages and colas contain caffeine and phosphoric acid, researcher Catherine L. Tucker and associates wanted to know whether cola consumption is associated with a lower bone mineral density in women. The table lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. So the data were collected through a prospective cohort study. All right, so take a moment, pause the video after you guys have put in all of these data values here for L1, and I want you to put in all of these for L2. I think you know you're already going to be running a line reg t-test, so if you want to go ahead and do that right off the bat, go ahead and do it and then come back to the video, please. All right, so welcome back after you guys have inputted all these into L1 and all the bone density into L2. So when we took a look at the scatter plot, you guys, this is the number of colas consumed per week. This is the bone mineral density, okay? And this definitely looks like there might be a negative relationship there. When you guys ran your stat line reg t-test, you got an R to be negative 0.806. That's pretty close to -1. See, but is it close enough to be to -1 for us to say that there is a linear relationship here? So that's what we have to test. Now we had 15 data values. So you go to your little table and you're going to look up what n equaled 15. Now when n equaled 15, we had a critical value of 0.514. Remember, if the absolute value of your correlation coefficient is greater than your critical value, then you say there is and in this case, would it be positive or negative? And it's going to be the negative. There is a negative linear relationship between the number of colas consumed per week and the bone mineral density for these women. So can the authors conclude that the increase in the number of colas consumed cause a decrease in the bone density? No, they can't. See, there's some other lurking variables in there. Guys, maybe the body mass index might affect their bone density. Maybe their height. Maybe they smoke or don't smoke. Maybe alcohol consumption, calcium intake, their physical activity. See, all of these things, maybe even the exposure to the sun could even be a cause. So we're looking for, see, there's lurking variables in there. So there's no way that I can say drinking sodas is going to cause your bone mineral density to decrease. We can definitely say there's a relationship here. There's a negative linear relationship, but I'm not able to say that it causes it because I need to be able to control all these other factors to be able to actually say this one thing is what caused it. So therefore, we always just say that there is a negative linear relationship between. We do not use the word cause. And that ends our 4.1. I'll see you guys later. Have a great day.